3.8, implicit differentiation. So far, we have been finding the derivatives for functions like f of x or y equals some kind of function, where y is defined explicitly as a function of x. So the question now becomes, what if we can't define or separate y, so we implicitly, so it does not specify y directly. So we have the situation of the equation of a circle. And I have the pictures here. So on the picture on the left is the equation of a circle, and it doesn't pass the vertical line test. It's not a function. So in this second picture on the right, we split or we solve the equation for y, and we split it into two separate functions. The top half of the semicircle, that is a positive square root, and the bottom half, which is a negative square root. And each function on its own then would pass the vertical line test. So that is solving it for y and putting it in terms of y. Explicitly in terms of x. But what if there's situations where you can't? The book also talks about one of a sideways parabola. For example, you might have x minus y squared equals 0, and you can have a sideways parabola, but in even this case, you can solve for y. So then it becomes difficult if you can't. So if you can't solve for y. So let's go ahead and look at some examples. So in the book, for example 1, implicit differentiation, I'm going to do example from homework 5. And I have x to the fourth plus y to the fourth equals 2. And then I want to evaluate it at the point 1, negative 1. So from here, I'm going to try to do the way the book does this first example, but I don't like it. And then I'm going to go do the way that I do like it. The book says the first thing you want to do is take the derivative of each part of this function. So they're saying, okay, d of the function x to the fourth in respect to x, and then the derivative of the function y to the fourth with respect to x. And on the right-hand side, y, the y is 2, I'm sorry, the constant 2, so the derivative of 2 with respect to x. Then the book says, well, wait a minute. Sometimes it might be easier to replace the y as a reminder that it's implicit differentiation if you plug in y of x. So they're saying, really, instead of doing this, you should really have y of x to the fourth in here so that you can remind yourself that you're going to have a chain rule issue going on because it's not in the correct notation. So the book says, okay, let's walk through this. And they take the derivative of x to the fourth with respect to x. Good, boom, we're done. All right, but then the next term, it becomes the tricky one. It's really that derivative of y to the fourth, but because it's not with respect to x, I have to have it times the chain rule of y dy dx. And then from here, I'm going to go to the derivative of the constant, which is 0. The next step is to go ahead and solve for dy dx. So if I did that, I would be subtracting subtracting 4x cubed from both sides and then dividing by 4y cubed. So I would have dy over dx equals negative 4x cubed divided by the 4y cubed. Simplifying, I would get this as my derivative implicitly. So I have an x and y value left in the derivative function. So now the problem is when I go to evaluate, which was step B, so for B, they wanted me to evaluate dy dx when I use the point 1, negative 1. So I'm going to go ahead and plug my x and y values into this function. And we can see it should be a -1 over -1 or a value of 1. All right, let's do another one. I'm going to do number 10 in the book. It is the square root of x minus 2 square root of y is equal to 0, and I want to evaluate it at the point 4, 1. So from here, again, we can't just solve for y easily. It will just take the derivative implicitly. So I'm going to go ahead and knowing our formulas for the derivative, I'm going to go ahead and say the derivative of the first term, and then the derivative of the second term, but I'm going to, instead of replacing the y with the y of x, I'm just going to say whenever it's a y, you have to do the chain rule of multiplying dy dx. So the derivative of this times dy dx. Derivative of 0 is 0, and then from here, I can simplify this, and I'm going to want to solve for dy dx. I should get dy dx. I'm going to subtract the 1 over 2 times x, the square root of x, and then I'm going to multiply it by the reciprocal of the y. So it's going to be multiplying it by a negative square root of y. And then I simplify it, and I get the square root of y is over 2 times the square root of x. Now, if I want to evaluate it at the point 4, 1, I've got the square root of 1 over 2 times the square root of 4, or 1/4. All right, I want to do one more example and show it to us in with a trig function implicitly. So I have cosine of y is equal to x, and I want to evaluate it at the point 0 pi over 2. And I'm going to go ahead and do implicit differentiation. So I'm going to be taking the derivative of cosine of y. So the derivative of cosine of y is negative sine y, and chain rule times the dy dx. Derivative of x is 1, and then I'm going to solve for dy dx and have dy dx equal to -1 over sine y. I can still evaluate this using my point. And then from here, I see it's -1 over sine pi over 2, which is -1. All right. Next, I want to find the tangent line with implicit differentiation. So this is really nothing new from what we've been doing. The only problem is I'm going to have to use implicit differentiation to find the derivative, find the slope, and use the point that we're given to find the equation of the tangent line. So we're going to do number 25 from homework, which is x squared plus xy plus y squared is equal to 7 with the 0.21. So just finding the derivative of this implicitly and then the slope, we can then find the point or the equation of the line in part B. So implicit differentiation, derivative of the first term. Second term is product. So I'm going to do derivative of the first just times the second function plus derivative of leaving the first function times the derivative of the second function. But the derivative of the second function is y, so it's going to be 1 times the chain rule dy dx. Moving on to the third term, I have 2y times the chain rule dy dx, derivative of 7. From here, remember, I'm going to want to solve for dy dx. So in this case, I'm going to go ahead and I'm going to subtract my first two terms, and I will have x dy dx plus 2y dy dx. And then I have minus 2x minus y on the right-hand side. I'm going to do a GCF of the two terms on this side. And notice I know the dy dx is what's in common, but I'm putting that as the factor after, the second factor, after what I've factored out, because I want to leave that dy dx on that side. So from here, I'm going to divide both sides by the quantity x plus 2y, and I'm left with dy dx is equal to negative 2x minus y over x plus 2y. Notice this does not simplify any further than this because you would have to factor it. There's just no way it simplifies. All right, from here, we want to go ahead and find the equation of the tangent line. So for part B, my slope is when I evaluate this derivative using the point 2, 1, oops, sorry. And I should get a slope of negative 5/4. All right, from here, I'm also going to use this point 2, 1 and these two pieces of information in my point slope formula. To find the equation of the line. I'm changing this value of 1 of a 2 over 2 to make things simpler. And then I have my final answer here. Oh my goodness, my equations are messy with my board off today. And here's the equation of my tangent line. Solved for it implicitly. All right, moving on. We want to do higher order derivatives of implicit functions. So I'm going to do example 32. We have 2x squared plus y squared equals 4. So we're going to go ahead and I want to find the second derivative of this function. So I'm going to go ahead and find the first derivative, dy dx. All right. So I'm going to go ahead, so this is what I'm looking for. I'm going to take the first term's derivative plus the second term's derivative, remembering the chain rule, and the derivative of the other side. Solving for dy dx. Simplifying it when you can, and this would be its derivative. So here's the step. I want to take the derivative of that answer and find the second derivative. So my next one is to find the second derivative. But I see that I'm going to then have a quotient rule going. So I'm going to still do my high, d high, low, d low. So I've got my high function, the derivative of the high function, my low function, and the derivative of my low function. So I really have it 1 times dy dx. So I'm going to have to make sure I do my substitution with that. So from here, if I want to go ahead and take my derivative, let's go ahead, I'm going to do another color. I've got low b high minus high d low all over low squared. So from here, I can simplify, but now I have this dy dx in it when this is really what I need on this side. So the problem becomes, this is, remember, taking the derivative of this and saying the derivative of this dy dx is the d squared y over dx squared. And then we have to take the derivative of this side. So we've taken the derivative of both sides technically. So the problem becomes, what do I do with this extra dy dx in here? And that's where I'm going to resubstitute in this answer in for that dy dx. And then I'll have everything on the right-hand side in terms of x and y's. So I'm going to go ahead and do that. And I have y, we'll simplify this while we're going. Negative 2y plus 2x times the negative 2x over y over the y squared. I'm going to make a common denominator in through the numerator, and then I'm going to have to simplify my denominators again. So in effect, I'm multiplying everything, numerator and denominator, with a y, and it should simplify in to negative y squared minus 4x squared all over y cubed. And then this is the second derivative of my implicit function. We implicitly found this derivative of this function. So then when it says power rule for rational exponents, it seems silly that they stick this theorem in at this point, but we're going to use this for implicit differentiation. So I'm going to go through an example that is just an explicit differentiation using this rational exponents rule. So we're going to give them this function, which is the cube root of x squared minus x plus 1. And you know I can change this into a rational exponent. I'm sorry, 1/3. And then I can take the derivative of this. And remember, we're following the same rule, and we're really going to just be subtracting the 1 from here, and it's going to make a negative 2/3 exponent. So that's going to push us back down into the denominator to make a positive 2/3. The problem is I do also have a chain rule going on here. So with this, I'm going to multiply this by a 2x minus 1, and then this is my derivative. All right, that's explicitly deriving, but what about implicitly deriving something with a rational exponent? So let's go ahead and do number 46. Given x to the 2/3 plus y to the 2/3 is equal to 2, and we'll evaluate it at the point 1, 1. So doing our implicit differentiation, I have 2/3, and then 2/3 minus 1 will be an exponent of x to the negative 1/3, or putting it back into my denominator, there is a positive 1/3. Then the second term. Same situation, but remembering because it's y, we have a chain rule of dy dx. Derivative of the next side. We're going to go ahead and we're going to solve for dy dx. I'm going to subtract the 2/3 x to the 1/3. And I think at this point, maybe I will, I could put it in radical form. So I'll go ahead and say the cube root of x. And then I'm going to want to multiply by the reciprocal of this expression. So I'm really multiplying by a 3 cube root of y over 2. From here, I can see it simplifies, and I should have a negative cube root of y over the cube root of x. And then we can go ahead and evaluate this one, dy dx, at the point 1, 1. And when we do that, we see we have a negative 1 over 1, or negative 1 is our answer. The last thing I need to talk about is normal lines, which we have not talked about yet in this book. Normal lines do have an application. At this point in the book, though, for homework question number 63, we're going to do, remember the normal lines are the parallel line at a tangent point. So given an equation that is the equation of the tangent line at some point P, we could say, the normal line is the perpendicular line through that same point P. So exercise 63 says refer back to the tangent line that we found in problem number 25. Remember in problem number 25, we found the equation of the tangent line to be this, and we were using the point 2, 1. So in this situation, to find the normal line, I want to use the perpendicular slope, remember opposite reciprocal, which is 4/5, and I'm still going to be going through this same point 2, 1. So now the normal line's equation will be y equals 4/5 times x minus 2 plus 1, and I'm going to go ahead and simplify from here. Y equals 4/5 x minus 8/5 plus 5/5. Changing my 1 into fifths and having this as my equation of the normal line. And we're done.